nuts or not. We might try it, and you can tell me afterwards it drove you nuts. But actually, we did this problem. So let me go back to what this problem is. You might recognize your handwriting up here, right? So this is a salt solution, and somebody made it up, and they told us what the concentration was in grams per liter. That's grams of salt per liter of solution. And that's not the number we start with when we work the problem. That's like a physical property of the solution. They said what volume, so we're trying to get to volume, would contain 22.3 grams of sodium chloride. So this is how you guys worked it, and which was great. Okay, so the term you started with was the mass of salt you wanted. Then you used the grams per liter. Notice that we had to flip it, right? We flipped the concentration of sodium chloride to get to liters of solution. And then you guys did this one, where now the concentration of the solution was given in terms of molarity. So one of the first things you guys need to do if you're faced with a problem that has a big M in is you need to unpack what that big M means. So in this case, the analyte or the thing that's running around is the K2CR2O7. So 0.255 molar means 0.255 moles of K2CR2O7 in 1 liter of solution. And that's not the term you start with. Okay, and then it goes on to say, it says, if an experiment calls for 0.015 moles, okay, how many milliliters of the solution will you need? So to get from moles to milliliters, actually from moles to liters and then liters to milliliters, you use the molarity. So you knocked it out this way. Okay, so you started with the moles, use the molarity, okay, the flipped version of molarity, okay, to get to liters, that one in terms of milliliters, and you knocked it out. So we're going to do another problem, okay? So this is where we pick up, right? So a different analyte, a different salt running around in water, calcium chloride. How many moles of calcium chloride are there in 75.0 milliliters of a solution that has a concentration of 0.108 molar? And there in the pink is kind of unpacking that. Okay, so if I were to diagram this, and again, excuse the finger, so we'll try it today. But notice that we're basically going to go from 75.0 milliliters, okay, and we're going to probably have to go to liters first. Does that make sense? Actually, I think it's on the next slide, isn't it? So here's what we're going to do. We're given milliliters. We want to get to moles. So we're going to go from milliliters to liters, okay, using the metric system. And then we're going to go from liters of solution to moles using the molarity. So, you guys want me to pass it around or just, you guys don't care?
Yes, please pass it around.
You know what? I was going to start with Chelsea, not fight with Chelsea.
Way to go.
You're so nice.
Yay. Okay, and also I decided this time we're going to try without the stand. But see this thing kind of wiggles up and down? Mm-hmm. So if you just kind of lay it on the table. Okay. Yeah, just kind of lay it there. I think we might like that. We'll try that.
Okay. So am I going to need to find the molar mass for this equation?
No, the funny thing is, in a problem like this, I'll kind of say it to everybody, in a problem like this, you don't find the molar mass. Oftentimes, there are times in solution problems that we don't need to go from grams to moles or moles to grams.
Okay.
I'm liking it.
Did you get to 125?
It's in the problem. I don't know what to do
It
next.
was in the problem.
Oh, I'm doing the wrong one.
Then you're going to use the molarity, which is that, what was it, unpacked up here. Okay, on the previous slide it said that this is
okay.
0.08 moles per 1 liter.
So
So we want liters to cancel.
you're going to want 1 liter, and then you're going to want the 0.108 on top.
Right. Does that look okay?
Where's the 125?
That was in the problem. That was,
Oh, I'm looking at the wrong problem.
oh.
Yeah, that's my
That
fault.
wasn't the problem. It's the eraser right here. Yep. And
Yeah,
then
right.
click this one.
You didn't know, David.
Yep, looks good.
Oh no.
That's why they were looking at us like, what?
I can't read. Okay.
Okay, is that better?
That's a
So
75.
75, 75.0, 75.0. Is that the problem then?
Yes, up here.
Okay. Okay, David, you got a calculator or a bar calculator?
There you go, bud. Right there.
I think so.
Oh, you like it. Okay.
So,
Shit.
Gosh, I can't read.
I feel like we should have drum rolls.
Is it?
How much big should you think?
I only did 2 right, cause 75.
No, it's 75.0.
Shit.
So,
Did you clear it?
Hmm. I don't know if that's right.
Let me see.
do we have confirmation?
Where's that?
No.
Erase button's right there.
All right,
That's what I got.
very good. Well, it looks like it's
I don't
good.
trust my calculator.
Any questions about that? Okay, let's take a look at the next problem. Yeah,
Good job, bud.
it's funny because we do so much with using the molar mass to go back and forth between grams and moles that when we hit this sort of problem, we're like, no, you don't need to use the molar mass. Okay. All right, the next problem. What mass of glucose, and then they give the formula for glucose. So now we probably do need to use the molar mass. Okay, so what mass of glucose is there in that volume at that molarity? So, thank you. So just to kind of fill in then, you have this at the top of the next page. So Andrew, I'm going to turn this over and have you write out the molar mass. We haven't done that for a while. But you see, because it said grams, that we're going to need to use molar mass. So we can use the volume to go, we'll need to convert the milliliters to liters, and then we can use molarity to get from liters to moles. And then we can use the molar mass to get from moles to grams. So before we start, we'll kind of knock out the molar mass, if you don't mind, Andrew. And even if you do mind. You guys are going to have these average atomic weights memorized, aren't you? You're dreaming it.
I didn't do the Elvis song yesterday.
You what?
I heard the Elvis.
Oh. I wonder if you were a biologist, if you would like have some molar masses memorized. Probably. Two decimals is good. sir. All right. We're ready to knock it out. Oh, sorry. Let's just knock it up down there at the bottom where it says more mass. But so, just want to do the whole thing? Sure. Let's go ahead and give you a writing utensil. Okay. Hold on. There's the 100. Seems like the last few times we've done this, Tyree, you've had to set it up like this.
I know. It's pretty nice today.
Look at the draw. Look at the draw. We're going backwards. I feel like counterclockwise. There's no stylus.
Your stylus?
Finger.
Oh, okay. Sweet. Okay.
Found it.
Looks like 3.
Yep.
And that is.
Perfect.
Do I need to put in?
No, I'm fine with that. But I'm so gross. Very good. Any questions? I'm liking it. So the whole problem with chemistry problems is there's all sorts of different variations, quite honestly. So, like I really need to tell you that, right? So we're going to work this problem, and I'm going to kind of talk you through a few things, I guess on the next slide. But before I go to the next slide, one of the things I want to point out, the next slide is going to have Jason and Matthew unpack these numbers. Okay, what do they mean? But the other thing I want you to recognize is what is your goal, okay? This is your goal. It says what is the molarity of the solution. So sometimes I'll write down question mark, that's what I'm trying to find, molarity, and what that means is moles of moles of acetic acid, CH3COOH, per 1 liter of solution. That's what we're trying to get to. That's our target. And we're going to use the weight percent and the density to our advantage. So on this, we'll start with Jason. I want you to unpack, when we say 76.0% acetic acid in the solution, what does that mean in terms of like a ratio? Usually I say something over 100 grams of
It would be 76
Mm-hmm.
grams over 100.
76.0 grams of, and this would be the CH3COOH. Okay. Over 100 grams.
Would be that same thing.
That would be of the whole solution. But if you ever want the eraser, it's that one at the end there. Guys, you do good. And then you need to click the red pen again. Got it. Okay. so that's a physical constant. Now, the problem here is we kind of have two physical constants, okay? So, all right, Matthew. So the weight percent, the trick comes when you unpack this. The grams of what? So 1.07 grams. Nope, the other one. Actually, it's grams of entire solution.
Grams of solution.
Mm-hmm.
Per 1.
Milliliter. Very good. So the thing about it is, anytime somebody takes a density, they're taking the density of the whole solution. They're not really just kind of, this is an aqueous solution. So part of it, most of it's acetic acid. What, 24% of it is water. To get the density, they take the density of the whole mixture, the whole solution. Okay. So we're going to use those to our advantage. Remember what our target is. Okay, I'll just kind of add that too. Our target is molarity, and that is moles of acetic acid, CH3COOH, per 1 liter of solution. All right. So I'll go ahead and, for that milliliters, I'm going to add milliliters solution. So if you kind of start looking at what we have, we can make grams of solution cancel if we, do you see where it's in the top here and it's in the bottom there? If you just kind of line these up as they are, it looks to me like grams of solution are going to cancel. Does it seem right to you? And if we line them up, grams of solution will cancel and we'll be left with grams of pure acetic acid per 1 milliliter. And we're close. We need moles, not grams. So we're going to have to knock out the molar mass of this stuff. And that is on this slide. So now we're going to pick on Heather. Did you? Oh, it's already there. Yeah. Good. Okay. So you guys already have the molar mass. I don't have it up here. I'll just write it down. 60.05 grams per mole, okay? Okay. So I can't remember what my next slide is. So I'm ready for you, and I think Heather's been working on it. Heather, do you have a solution to how to kind of use the weight percent and the density and the molar mass to get moles per liter? Mm-hmm. She lined up those other two terms. So grams of solution cancel. Why don't you go ahead and write that down, and then we'll pass it on to Alexis. So Alexis, watch. We're gonna pass it over to you next. So I'll say it one more time. The problem is you have grams of two things. You have grams of the pure acetic acid and you have grams of solution. So it's going to be important that you label which grams you're talking about. So that's from the weight percent. That's from density. Okay. So if we're just purely focusing on labels, grams of solution have canceled, and now we have grams. I'll turn my attention to Alexis. Now we have grams of acetic acid per milliliter. So you can either fix the grams to moles or you can fix the milliliters to liters. Anyways, because then we'll give it a Chelsea and Dave. Oh, she's going for the liters. I like it. Everybody buy that? So now milliliters have canceled, and it's from the second term in the denominator to the third term in the numerator.
Do you want me to go on or just?
Now we'll pass it over here. Very good. So unit-wise, milliliters have canceled, and we're left with grams of acetic acid over liters, but we want moles of acetic acid over liters. So one more term should get us there. And then Davey,
So. What?
you can use that 60.
But that's gonna go. That's yeah. Okay. Oops.
Just put A, yeah.
Okay. Do you want me to solve it, or do you do?
That's my job.
Okay. Don't want to steal your pride and joy from you, David.
By all means. You don't have to do that?
No, I'm saying
How many sig figs you gonna give it?
3.
Yep. All right. Oh, and then what's the units? Because it's moles per liter. Yeah, moles per liter. Very good. Any questions? Okay, so grams in the last term of the molar mass canceled with, I should say grams of acetic acid, sorry, canceled with grams of acetic acid in the first term. Score. All right, high five.
Not so much.
So actually, I have some hints for these, but we're going to go ahead and I'm going to wait till hints at the end, and also post the kind of the screenshots. But these are going to be solution concentration problems. The first set of 3 sets. I know. Hey, it's a weekend. What else are you going to do? Okay, so we're going to work on dilution problems now, and I'm going to try to kind of describe how basically you take a stock solution, part of a stock solution, and you transfer it over to an empty container, and then you dilute it up with water. Okay, so you have a stock solution, you have a diluted solution. And you might be wondering, well, why didn't you just make the diluted solution right away? And here's the thing, that if you're after a really dilute solution, it's hard to go to our balances or any balance and to try to kind of carefully measure out 0.00034 grams and dilute it up. What's much easier is to take something you can sink your teeth into, some mass, make a concentrated solution, and then take a little bit and dilute it down. So it's called serial dilution. So we're going to work a problem, and I'll kind of show you this semester kind of how I do it anyway. So I mentioned the stock and the diluted solution. My stock solutions are going to appear in beakers, okay? And underneath there, I'll say stock. I've read this a few times, so I know what it's talking about. If you're like me, you have to read this a few times. You're like, what the heck? So it says 25.0 milliliters of a 0.160 molar calcium chloride solution. Now, if you read it a few times, you're going to realize that they're talking about this is the stock solution. The stock solution has a concentration, I'll change my pen so I can see better, of 0.160 molar CaCl2. Okay, that's my stock. And it says they transferred, probably used a pipette, just like you guys used 10 mil pipettes, they used a 25 mil pipette. So 25.0 milliliters of the stock was transferred over. And then it's transferred over to probably a volumetric flask. And I think we've seen these in here. They have tall necks with one calibration mark. And this calibration mark happens to show where you dilute it up to get 125.0 milliliters. Okay, so this one over here on the right is my diluted solution. So I'm kind of setting up the problem. I'm just stalling. Okay, so, and the word aliquot, I love the word aliquot. So that's the 25.0 milliliter aliquot of stock was transferred to this waiting volumetric flask. All right, blah, 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 blah. And then it says that they went ahead and filled up to the line with water for your, okay, so it just means that, okay, they filled it with water. There's not a question yet. Okay, so here's the question. The question in chemistry problems like this take all sorts of different forms. This particular one says, what is the molar concentration of your diluted solution? And so I like to usually break these down at least into two parts. And so what you're going to see, what we're going to work together, let's see, what do we, David? So we're back to Andrew, right? Okay. We're going to work together. I like to first focus on what, in this case, what moles, what moles of calcium chloride were transferred in that 25 milliliter aliquot, knowing that it was that molarity. Okay, so you have volume and molarity, you can get to moles. I usually separate it out like that. And then my second part of my problem, I'll tell you ahead of time, is I'm going to take those moles and I'm going to divide it by the new volume, which is 125.0 milliliters. So if you don't mind, we'll kind of approach it that way. So then this is the question to you, Andrew. Knowing that your transfer volume was, I'm liking that, was 25.0 milliliters. But one more term then.
So the molar mass is what we use.
Well, it's going to be the volume. So usually I take the volume and convert it to liters and then plug that in. It's the same diff though.
Oh, okay.
Yep. And then plug in the molarity. Yep. So the moles of calcium chloride in that transfer aliquot. You know, thank goodness for spell check, because I don't know if I could really spell the word transfer correctly.
Can I just put aliquot by the 20 by the milliliters?
No, you just leave it. That's milliliters.
Can I just leave it?
Fine.
Okay.
He was asking like how explicit you need to be with your labels, and I think this is pretty good. Very good. So he's going to get the volume into liters, and then he can plug in the molarity. Very good. Cool. And I guess we're over to Kelsey to plug it to get the, thank you. Well, okay.
Is that right?
So 3 sig figs, you think so? 2 more digits after that. Very good. Well, good. Any questions for Kelsey? Gave it 3 sig figs. Perfect. Okay. So that's the moles that went flying through the air and they ended up in your volumetric flask. Okay. So then on this slide, the second step, go ahead and with those moles in that new volume, what's the molarity of the diluted solution?
So it start off with the 0.004, right?
0.00400.
0400.
At true trailing zeros, very good.
0, and then is that over 1?
And then I usually just put the volume down there, the new volume,
New volume,
the new diluted volume.
right underneath it?
Mm-hmm.
Okay.
Yeah. I'm liking it, yep,
Is that it?
almost. And then molarity, you need to, once you while you have it, go ahead and get liters in the bottom. I'm gonna pass it over to Jason.
Say the liters in the bottom?
Uh-huh.
Okay.
Yay, very good. So units of mils cancel, and we have units of moles per liter, which is what we wanted. And so you can either go with a big M, or you can say moles per liter. Very good. Any questions? I'm liking it. That's your diluted solution. With all chemistry problems, you should say, does that make sense? And it seems reasonable to me. You would never want this concentration to be greater than your stock, right? Something went wrong with your calculation. Good. Okay, I don't think, we'll try it. Okay, that's okay. This actually, the movie that didn't play actually is summarized here. So just kind of like we've been talking about, this would be our stock solution, okay, kind of in the problems that we're working. And notice a good way to get a nice precise volume of transfer is to use a pipette. So there's a pipette with a little calibration mark like you guys have been using in the lab. And then he or she carefully then puts it over in where the diluted solution is going to be, touches the tip to the side so it runs out properly, does not squeeze the last amount out because it's to drain. And then once it's all transferred, they go ahead and dilute it up to the calibration mark on the volumetric flask. But before he or she gives it to another person to use, they are going to invert it a few times to make sure it's all mixed up. That's gotten me a few times. Because otherwise, if you don't do that, there's a good chance that you've got concentrated solution down here and dilute up. Okay, well you knew it, just we have another one to do. And so to kind of tell you what this one looks like, I'll kind of draw the stock and the diluted up there because it's very similar. I'll let you kind of read through it a little bit. Okay. So there's my stock. And in this case, they said that 2 milliliters of a stock solution was added to a volumetric flask that has a capacity of 500 milliliters. So here's my volumetric flask. Here's my calibration mark, 500 milliliters with 4 sig figs. Okay, and here's my transfer amount, 2.00 milliliters. All right, what else we got? Looks like it it says that they tested the resulting diluted solution, and they packed it up in scientific notation, the molarity. So over here, we have, I'll change color so we can see it better. The molarity is 1.60 times 10 to the negative fourth. And the analyte is that K2CR2O7. Potassium dichromate. Well, there's no question up here. That's just stating the facts. The facts, ma'am. So the question is down here, what was the concentration of the stock solution? Question mark, big M. Question mark molarity for the stock solution. So again, we're going to break it up into two parts, and we're going to kind of pass it around. If you look at this a little bit, can you see where, honestly, I'll change my color to orange. Over here, we have volume and molarity. Do you see where we can get to moles of our diluted? So we can get to the moles of the diluted. And guess what? Those moles only got there through that 2 milliliter aliquot. So once we have to transfer moles, then all we got to do is divide by that volume of 2.00 milliliters. And boom, that must be the concentration of that stock solution. So that is what we're doing. Where did we leave off? Okay, thank you. Okay, Matthew. That's my brother's name. Did I ever tell you that?
No.
Yeah. Really? See? Or it's a club. So, could you kind of set it up where we're looking at the diluted solution? We know it was 500 milliliters, and we know its molarity, and I want to get to moles. So, I would start with the 500.0 milliliters over 1.
Yeah. Do I have to specify since it's only one thing?
Right. No, you don't have to specify since it's only one thing.
All right. And then we want the molarity, which is moles per liter, so we got to go to liters.
Yep, very good. Heather, get ready.
And then from that, we have the liters on top, so per 1 liter, we have 1.0, or 1.60.
Impressive.
To the negative fourth.
Negative fourth, perfect.
That's a 4 over there.
Okay, good. And moles per liter. I'm liking it. So milliliters cancel.
That's moles up there.
Oh, that's moles.
It's a 4 and moles all combined.
Oh, that's right. Very good. Milliliters cancel, liters cancel, we're left with units of moles. And Heather has tapped it out on her calculator. Well, it looks reasonable to me. Very good. Oh, and that's just moles, though.
Wow.
Perfect. Thank you. Okay, Alexis. The next slide says, if that's the moles and we know the aliquot was 2 milliliters, then do you know the molarity of the stock solution now? Oops, I need to give you a pen.
Is that right then?
Oh yeah, that looks really good. Oh, assignment slide coming up next. So Chelsea, are you tapping it out on your calculator?
Can I just leave it like that? I need to label it like how I have it there.
Right.
I do need to do that?
No,
Okay.
you don't need to. That's a really good, people are asking, do you need to put the K2, CR207, and as long as you only have one solution, you're fine. In Monday's lecture, we're going to have 2 different solutions, so we'll have to be explicit.
That's right. I was like, you're staring at it.
Yes. Psych. Dee, 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 dee.
Oh, man. That's what my calculator got, but it is weird.
You got set up. No. So we need to just double check about your calculator. I think okay, here's the deal with your calculator. So
Okay.
make sure, like, when you take 8 times 10 raised to the negative fifth, you have to use, remember we said you have to use, where's your E?
It's,
No, that's your E raised to the X key.
I have no idea.
Okay. Well, for now, what did you get?
0.4.
0.4
Molarity.
moles per liter.
Like that?
Okay,
Or-
yeah. I can see that because it's 10 to the negative fifth and 10 to the third, and I buy that. Does that look right? Okay, other than sig figs, what did you get?
I got .04.
Oh, I think
Okay.
it is 0.04. Close. Final answer, because that does sound familiar. Thank you. And then go ahead, can you give it, while you're at it, 3 significant figures? Because right now it just has 1.
So
So
can I
you're
just put a
trailing
0?
zeros, yep. Another. One more. Good job, guys.
It really is.
Okay, any questions? So that's the answer. Isn't that adorable? That's the molarity of your stock solution based upon the concentration and the volume of your diluted. I just think that's so cool. But what's not cool are you get to add these to be due Monday. We're gonna finish we have just a little bit to go, and I'll show you how kind of straightforward, I wouldn't say easy, the last topic is. Okay, so these are also due Monday. Ready? All right. So we talked about compounds. Compounds you write a formula for, and you say like H2O is the compound for water, NaCl is the compound for salt. There's 2 types of compounds. There are ionic compounds and molecular compounds. And we're going to talk about that more, I think, in the next unit, or the last unit, I can't remember. But ionic compounds, they dissolve in water and break out into their ions. And they are great then at conducting electricity, okay? Pure water, if water has no like little ions in it, it does not conduct electricity. Isn't that weird? Okay. So ionic compounds, when they dissolve, here's 2 examples of ionic compounds. Sodium chloride and calcium nitrate. You know it's dissolved in water, right, because the AQ, okay? The arrow is showing it falling apart. We use the word ionize for basically it dissolving in water. So here's the catch, and this is the part that goes a little bit with stoichiometry we've been talking about. So do you see where 1 formula unit of this will break out into 1 each of those ions? Now, I realize at this point in the class we haven't talked about Na is going to be a plus, or specifically a +1. Cl is going to be a minus, specifically a -1. So for your homework, I'm cool with if you just at least recognize or at least try to see that Na and the Cl are going to break apart. Don't worry about the charges for now. Similarly, okay, kind of from left to right, I don't know if you can kind of see that the the Ca is going to break apart from the NO3s there. So notice then on the product side, specifically with regard to NO3s, since it's quantity 2, when 1 formula unit of CaNO3 quantity 2 breaks apart, we get 2 NO3s. Again, don't worry about the charge. I just want you to recognize we're getting 2 NO3 units. You good with that? Because there's going to be some homework. It might be sort of the homework where you just do your best, okay? but I do want to talk about this, and I think you will do well. So let's just say we were given the molarity. We're going to work a problem here, kind of like what you're going to do for homework. And the molarity is 0.230 molar of the salt. Okay? You dissolve it up, and it all dissolves, and you have Ca2 pluses and NO3 minuses running around. What this problem says is, what is the molar concentration of the NO3? Okay. Well, we've been working with stoichiometric ratios. Do you see, by the way, what is the number, what's the coefficient in front of the calcium nitrate? It is 1. So do you see from this, I could say that 1 mole of CaNO3 per every, tell me what number to put up there. 2. Perfect. And that's it. That's how you work that problem. So 2 times 0.230 is what? 0.460?
Yep.
Okay, that's it. That's the answer. Molar of the NO3 minus. Again, if you can't recognize that there's a minus there, don't worry about it. And I'll kind of show you what the homework is. Are there any questions about that? One last thing, I'll show you when we get to the homework, but if you ever see, and you will for your homework, see something like this, something in brackets like that, what these square, big square brackets mean is molarity. Okay? So, so just keep that in mind. Okay, so these will also be due. So let's take a look at the homework right quick. And I have so much fun doing this at my desk before we come. Yeah. Okay. So just kind of starting with the one that we just did, it looks like this. Okay. So 7 and 8 look like this, where you see 7 has A through D. You are given the salt, and you have to show it break apart. Oops, sorry. And I did one for an example. So the example I did looked like this. I picked, and again, I'm going to post these, but I just picked C. And the C says that it's Al2SO4 quantity 3. So what I'm hoping or counting on you being able to do is to recognize that I basically have a split there between my Al and my SO4. Down here, I'm showing you have 2 Als and 3 SO4s. So to work that, if you recognize that for every 1 Al2SO4 you have 2 moles of Al, then you can go ahead and work that problem. So that'll be posted. Then if we take a look at your other ones, and again, I think some of you are anxious to go. If we go back to the first problem set, it looked like, I think this was the first problem set. Okay, where I'll just put all of these up there. It only does what you ask it to do. Okay. There's a second question. It's kind of like, yeah, those are your hints. Third question. So I guess I'm just going to kind of leave you to it in a sense, but know that these will be posted out there for you. How's that sound? Okay. Have a great weekend.
Can you go back to that first slide you showed us, please?
This one?
No, that one.
Like with the 7 and 8 one?
Mm-hmm.
I can't.
Can you put down the rest of the slide? So is this just 2 moles because there's... Where's that? Oh, is it 2 moles just because there's 2 right here?
Yes.
And then this is this gonna be times?
3, yeah,
So
so
it'd be
there's a
12?
3.
It'll
Well,
be 12 for oxygen.
it would be, but in this case, we're kind of having them stick together, and the questions are always,
So
what's
then
the
it's-
molarity of
Okay, so then it will be 3 for this?
3 units of SO4s?
Yeah.
Mhm.
Okay.
Yeah.
All right.
Yep,
Thank you.
welcome.
Okay, so it's
You too.
asking the molarity of potassium and the molarity of,
Right.
okay,
That's why I kind of said the square brackets are molarity, yes.
okay.
Yep, yep.
Have a good weekend.
Thank you, you too, Alexis.
I was right on the answer.
You're what?
The one that was 0.4,
Yeah,
she says 0.04.
yeah. You were right?
Yeah.
Oh, good for you. Have a good one, Andrew.